Hello guys, so let's continue talking about maps, and this is lecture 7.2, kernel, image, and isomorphism. Okay, so let me remind you the following well-known definition, or bunch of definition, reminder. So when we have a map F from between two sets A and B, then there are three important definitions. So there is a notion of F being injective. So injective is a map which takes different elements here to different elements here. So for every A1, A2 in A, such that f of A1 equals to f of A2, this implies that A1 equals to A2. So this is one important type of map, and then it just means that basically A sits inside B in some sense. So this is what happens. Another important case is F being surjective. And this is when for every element B in B, there exists A in A such that f of A equals to B. So usually maps are not surjective, but then there is a notion of an image of the map. So image of F is just a set of all elements B in B such that there exists A in A with the property that f of A equals to B. So basically, for instance, if you have an injective map, then this will be the image. And F is surjective if and only if image of F is the whole set B. So that is clear from the definitions. And finally, F is bijective if and only if F is injective and surjective. So then it's called a one-to-one correspondence, and the reason is that actually though map is defined as map from A to B, there exists another map going backwards. So maybe a little fact is that F is bijective if and only if there exists another map G such that F composed with G and G composed with F is identity. So this is called the inverse, and basically it is just the same map. You come from here, there. The fact that it is surjective means that you can actually define it for every element in B, and the fact that it is injective means that this map backwards is actually well defined. For every element there is just one pre-image. So this G is denoted usually by just F inverse. And then there are tons of properties like composition of injections is an injection, of surjections is a surjection, of bijections is a bijection. So I'm not going to talk about all that in all details because probably you have seen it many times. But what I will do, I will apply all these ideas towards linear maps. And then we will introduce what is an image here, what is a kernel. So this is related with the fact how linear maps fail to be surjective. This is related to the fact how they fail to be injective. And isomorphisms are just bijective linear maps. Okay, so let me start with image. So here is the idea. So if you have a linear map, so little definition, so L is a linear map, then one can define the following things. So firstly, then image of L is just the usual image of L. So let me just repeat the definition. So L is a linear map, L is from V to W. And then image of L is just the set of all vectors W in W such that there exists V in V with the property that L of V equals to W. So this is what is the image, and here is an example. For instance, if you take a map from R2 to R2, sending xy to x0. So this is just takes a plane and drops every point. So whatever the y coordinate is, we just forget it and move it backwards. So move it downwards towards the x line. And so this one is not bijective and not surjective. And the image of this L is just the line. So the subspace x, 0 for x in R. So that's an example of the image. So the main property of the image is that image is a linear subspace of W. So let me formulate this fact. So this is an important proposition. Is that so L from V to W is a linear map, then the image of L is a subspace of W. And another maybe remark, it's the dimension of the subspace is called the rank of the map. So, for instance, the rank of this map is equal to 1 because the image is one-dimensional subspace of R2. So, let me prove it. That's really easy. So, proof is as follows. So remember, to prove something is a subspace, we need to prove two things. Sum of two vectors there is there, and when you rescale a vector there, we get a vector there. So, part 1 is for every W1, W2 inside the image, there exists V1, V2 in V, such that L of V1 equals to W1, L of V2 equals to W2. But then we can sum them up, and so we get that L of V1 plus V2, using linearity, equals to W1 plus W2, and so W1 plus W2 is in the image. So sum of two vectors in the image is in the image, and similarly, for every W in the image and lambda in F, lambda W is in the image, and this is similarly. So that's the end of the proof. So very simple statement. But what it tells you that there is a very nice way to construct subspaces of W. Just take any linear map, its image is a subspace. Next story, kernel. So image was about the maps being not necessarily surjective, and obviously image of a map equals to the whole space W if and only if the map is surjective. So what about injective maps? So let's give the following definition. So suppose L from V to W is a linear map. It's a linear map. So then the kernel of L is a set of all vectors V inside V with the property that L of V equals to 0. So it also can be called pre-image of 0. This is how pre-image of a map is defined. So kernel is exactly something which measures how far your map is from being injective. So let me first give you an example. So for instance, you can take you can take the space of polynomials, and as a map L from V to V, you can take the map sending a polynomial to its derivative. And then the kernel of L is of course just polynomials of degree 0. So these are polynomials of degree 0. And the reason is just because if the derivative equals to 0, your polynomial has to be constant. So that's an example of a kernel of a linear map. Maybe another example is, for instance, you can take this Fn map to F, which I call L, and L of x1 up to xn equals to sum ai xi from 1 to n. So this linear map, a1x1 plus a2x2 plus and so on, an xn, which we already discussed. And then one can ask, what is the kernel? And then the kernel of this map. So if not all ai vanish, so not all of them equal to 0, then kernel of L is a hyperplane in V. Okay, so next there is a very important proposition, which is actually more or less trivial about kernels. So let me formulate it here. So proposition. So again, L from V to W is a linear map. It's a linear map. Then two statements are true. So firstly, kernel of L is a subspace of V. So kernel is also a subspace, and this is the reason why we actually look at that. And second is that kernel of L equals to 0, 0 subspace, if and only if L is injective. So basically, if the subspace is big, the map is not injective. So little remark, so dimension of the kernel of L, some people call nullity, something like nullity of L. I'm not going to use this word a lot, but you can see it in the book, in books you read. So the bigger is this dimension, the further your map is from being injective. So completely crazy example is when you have this map from V to W, which just sends everything to 0. So then, of course, the kernel of this 0 map is just the whole space V. Every vector is going to 0. But more reasonable maps usually have smaller kernels. And finding kernel is, of course, as we will see later on, the same thing as solving system of linear equations. So this is related to things we already have seen. Okay, let me prove this proposition, and for this I will erase all this part. Okay, so proof. So I'm doing it right to left as usual. So proof. Okay, part 1 is almost trivial. So part 1, so we need to show that firstly, let's suppose that V1, V2 are inside the kernel. Then L of V1 equals L of V2 equals to 0. So then L of V1 plus V2 is just their sum. So it's also 0. So V1 plus V2 is inside the kernel. And similarly, for every lambda in F and V in the kernel, this implies that lambda V is in the kernel. So this is more or less trivial. Just when you sum up vectors which go to 0, their sum goes to their sum, which is 0. Similarly with rescaling. And this proves that kernel is a subspace of V. In particular, it always contains 0, because 0 goes to 0 under a linear map. So, second story, what about injective? So, that's also very simple. Let's start with this direction. So, assume V1, V2 are in V, and L of V1 equals to L of V2. So we need to show that these two vectors coincide. That's what injective means. So then L of V1 minus L of V2 equals to 0. So L of V1 minus V2 equals to 0. But this, of course, means that vector V1 minus V2 is in the kernel. And then V1 minus V2 equals to 0. Because we prove this direction. So kernel is 0, we assume that and prove it's injective. And this, of course, means that V1 equals to V2. So that's it. Very simple. And backwards, so this is first part. Second part, so let's assume it's injective. So if V is inside the kernel of L, then L of V equals 0. But this is the same as L of 0, because L is linear map. So we found two vectors with the same image, 0 and V. And since L is injective, so L is injective, this implies that V equals to 0. And so kernel is 0. And we are done. And that proves the statement. So you see, very straightforward, and you can use such proofs to practice with just this kind of linear algebra plus set theory story. Okay, so now we have these two ideas. So if you have a very general map, it has some kernel inside V, some image inside W, and that's what it looks like. So, of course, a very particular case is when your map is injective, kernel is 0, and surjective, image is the whole space. And then such maps are called isomorphisms. So let me talk about them a little bit. So, definition. A bijective linear map is called an isomorphism. So, of course, that's the same thing. So, equivalently, so L from V to W is linear. Image of L equals to W, and kernel of L is 0. So that's surjective, that's injective. Together it's bijective. So this is what is an isomorphism, and also two spaces, vector spaces, V and W over the same field are called isomorphic if there exists an isomorphism L from V to W, and the notation for this thing is V is isomorphic to W. So we put these two horizontal lines and then the curvy one on top. So isomorphic, you should think of this vector spaces as basically being kind of the same. And what it means that L basically relabels. So it sends vectors in V to vectors in W, it's bijective, it's linear. So basically you can think of it as just giving you notation for vectors in V. So now they look like vectors in W, and you know that you add and multiply on scalars these vectors in the same way as in V. So, okay, so why this is important? So first thing is this is an equivalence relation. So basically you can think of it as some sort of equality between vector spaces. Let me prove that. So for this we need a little fact. So basically here is a statement. So L from V to W is an isomorphism if and only if there exists M from W to V, also linear, so both maps are linear, such that L composed with M is identity, and M composed with L is identity. So sorry, L and M are, so these guys are linear maps, linear. And identity, of course, depends. So this one goes from W to V and then back to W. So this is identity of W. And this one goes from V to W and then back to V. So it's identity in V. So basically, it tells you that, of course, this M will be denoted by L inverse. So this is just tells you the same fact, which is true for bijections, is true for linear maps. So this fact is pretty obvious. So proof is maybe let me leave it as an exercise. Whatever. And the main idea is that if you have a linear map, which is a bijection, it definitely has an inverse. Let's take it, and then you easily prove that it actually is linear. So that's the key fact. And of course, backwards, if you have a linear map which has an inverse, meaning has such M exists, then your map is a bijection from the set theory fact. So that's why it's so easy. And this is one fact, and another fact is that composition of isomorphisms is an isomorphism. So if you have V1, V2, V3, and these guys are isomorphisms, then composition is also isomorphism and is an isomorphism. And this is totally trivial because you know that composition of linear maps is linear, and you know that composition of bijections is bijection. So that's why. So proof is composition of linear maps is linear, and composition of bijections is a bijection. So, and from this you can easily see that this isomorphism is an equivalence relation, because basically if you have, so let me maybe write that down. Okay, so corollary is that isomorphism is an equivalence relation. So again, equivalence relation is something you think as kind of different notion of equality between spaces. And the proof is, remember, there are three properties. So V is isomorphic to V, just because there is this map identity, which sends V to V, and this is clearly is an isomorphism. Because we already discussed it's linear, and obviously it's a bijection, so that's why. So if V is isomorphic to W, then W is isomorphic to V. That's second property. And that's also follows from previous fact, because if you have L1, if you have L from V to W is an isomorphism, then L inverse from W to V is also an isomorphism, as we discussed. So that's why this relation is symmetric. And finally, if V1 is isomorphic to V2 and V2 is isomorphic to V3, then V1 is isomorphic to V3, and this is just because take one isomorphism, second one, and take the composition. So just take the composition. Okay, so that's the proof, and basically I do it all very fast because all these things are completely trivial, and hopefully you have already some intuition for that. We talked a little bit about isomorphisms before. So as you remember, if now let's look at sort of like all vector spaces. So these guys are all vector spaces. So if you look at just literally all of them, it will be probably not even a set. because there is some set theoretic issues, but let's just do it vaguely. And then when we have equivalence classes, then of course all collection of all vector spaces will now be cut into this isomorphic guys. And for instance, here you have like R3, and it is the same, it is isomorphic to, I don't know, say polynomials of degree less or equals than 2, and blah blah blah. So these are all isomorphic to each other vector spaces. So clearly isomorphic vector spaces have the same dimension. And this is obvious because if you have a collection of vectors in one space and you apply an isomorphism, it moves to a collection of vectors in the other space, and then one can immediately see that linearly independent vectors here move to linearly independent vectors there, and generating set here moves to generating set there, and so on. So if two vector spaces are isomorphic, all facts about these vector spaces will be basically, if they hold for one space, they hold for another. And so, in particular, isomorphic vector spaces have the same dimension. So, miraculously, more strong statement holds. So, in reality, actually, spaces are isomorphic if and only if their dimensions are the same. So basically, just knowing the dimension is the same as knowing the class of a vector space up to isomorphism. And this is the main idea. This is why dimension is so important. So let me formulate this theorem now. So very important theorem. So V, W are vector spaces over F, and then V is isomorphic to W if and only if dimension of V equals to dimension of W. So this is the only condition to check to know that spaces are isomorphic. Okay, so this is the main theorem for now, and let's prove it. So as usual, it is true for arbitrary vector spaces, but we will prove it only for finite dimensional vector spaces, and we will prove actually a stronger statement. So I will just literally explain how to construct such an isomorphism. But before that, a couple of examples. So, like examples we have already seen. So, for instance, if you take a vector space V are, say, polynomials over F of dimension less or equals, of degree less or equals than D. So then we know that dimension of V equals to D plus 1, and then just it means that V is isomorphic to F power D plus 1. So that's it, as simple as that. So nothing to check, no, you don't need to construct it, you don't need to do anything, just instantly you see that. And maybe next corollary is every finite dimensional vector space V is isomorphic to Fd, where D is equal to the dimension of V. So that's another example. And remember, we had this finite subsets of a finite set. So then it is a vector space over F2. It had dimension n, so it's isomorphic to F2 power n, and so on. So from the point of view of being isomorphic, vector spaces are classified by just one number, their dimension. Okay, so let's prove the theorem, and for that I will prove very important proposition, which immediately implies the theorem. So proposition. So let's suppose that V W are vector spaces of dimension n, and E1 up to En in V is a basis, and F1 up to Fn in W is a basis. So we have a basis of V and we have a basis of W. So then there exists a unique isomorphism from V to W, which I will denote by L, such that L of E1 equals F1, and so on, L of En equals to Fn. So this is a beautiful fact. Basically, the idea is that if you have a vector space, say R2, and another vector space, which better to be the same dimensions, so actually the same R2, then you can take any basis in one of them, any basis in the other, and then there exists a unique isomorphism which sends one basis to the other. So, so this is a way to think about isomorphisms. If you want to make an isomorphism from R2 to itself, you just take two vectors which form a basis and find any other two vectors which also form a basis and move them there. And all other vectors will have to readjust and also move somewhere, and there exists a unique isomorphism with this property. So the proof is immediate. So proof is very simple. And how we do that? So remember from previous part of the lecture. So there exists a linear map. Let's call it L, right? L, such that L of E1 equals to F1, unique. And so on, L of En equals to Fn. And here we have used only the fact that these vectors are, so we have used only the fact that E1 up to En is a basis. We have never used the fact that F1 up to Fn is a basis. So now we want to show that this is an isomorphism. And one way to do it is to look at the kernel and the image. So claim is that L is an isomorphism. So first let's prove that the kernel of L is 0. So suppose vector V is inside the kernel of L, and this V equals to x1 E1 plus and so on plus xn En. And then of course L of V equals to x1 L of E1 plus xn L of En, which is the same as x1 F1 plus xn Fn equals to 0. But this is a basis in W, so of course a linear combination of basis vectors is 0 if and only if, so then all the coefficients equal to 0. And then it just means that V is 0. So kernel is just 0, so L is injective. And similarly we prove it's surjective. So for every W in W, we know that you can write it down in a basis. There exists some coordinates in F such that W equals Y1 F1 plus and so on plus Yn Fn. But then of course W is just the image of the vector Y1 E1 plus and so on plus Yn En, just because when you apply L, this is where it goes. And so so W is in the image, and so L is surjective. So you see basically to give an isomorphism is the same thing as to give a pair of bases and just say this basis goes to this basis. That's it. And of course, it immediately implies the lemma, the theorem, because for finite dimensional vector spaces. So, and that's just because just choose a basis and then such map exists. So let me say that. So now theorem. So suppose V and W are finite dimensional vector spaces, and then dimension of V equals dimension of W if and only if V is isomorphic to W. So that's the statement. And as I said, it's true for arbitrary vector spaces, but we will prove it just for finite dimensional, not to go into all this set theory nonsense we never discussed. So proof. So one direction is just choose a basis E1 up to En of V and F1 up to Fm of W, and you see that this n is definitely the dimension. So this is the dimension, and apply the proposition. That's it. Just then there is an isomorphism moving these guys to these guys, in particular V is isomorphic to W. And backwards, that's also very simple. Because so if E1 up to En is a basis of V, then and L is from V to W is an isomorphism. So this is an isomorphism. Then L of E1 and so on, L of En is a basis of W. And the proof is that's completely obvious. So just imagine this guy is a basis, and then suppose there is a linear combination of these vectors which equals to 0, then their linear combination lies in the kernel. Kernel is 0 because it's an isomorphism, so it was 0. And similarly for the image. So that's the proof of the statement, and this proves the theorem, which was the main theorem of this section. So in the next section we will talk about dimension of the image, dimension of the kernel, and how they are related with each other.